let's expand on the simple model that we saw earlier. Okay, and here's our expansion. We're now going to take into account some external conditions. There's a famous law of heating. I think it's Newton yet again. He's done so many things. Newton's or law of cooling. But basically, if you talk about temperature, for instance, you can heat something up, and then when you put it down to cool, it'll cool down, but it'll never go lower than the room temperature. Similar to if you put something in a fridge, it won't go below the temperature of the fridge. So there's this external condition. So the exponential graph on that decay, or grow if you're heating up, so it's like shifting the exponential graph up or down. So it takes into account this external condition. So the equation basically changes to be this. Instead of the P to T being a constant times P, it's a constant times P minus N. Now, again, I could go and differentiate, it was integrate, wasn't it? Like I did before. And there are two solutions to this. P equals N, which we call the trivial case, and we're not interested in, because that's rather boring. I mean, if P is equal to N, have a look at the actual differential equation, you get to P to T equals K times 0, which is just 0. So it's saying it's just never changing. So that's very boring. That's what we call the trivial case. We don't consider that one. We're more interested in this case, where we get N plus AE to the KT. So as I was saying, it's like getting that basic exponential and shifting the curve up or down. So basically changing where that horizontal asymptote would be. So P is still population, but N plus A will now be the initial population. K, growth or decay constant, and T is time. So, very old question, but again, the classic question about temperature. So T is the temperature inside the room. A is going to be the constant outside air temperature. I thought it was Newton. Newton's laws of cooling states that the rate of change of temperature is proportional to T minus A. Show that T equals A plus CE to KT satisfies it. So it's like I was saying this morning, they don't tend to get you to prove it via the integration. They tend to say, look, show it works, show it satisfies. So here's the equation. T equals A plus CE to the KT. If I differentiate it and get dt, I get KC e to the KT. I want to show it's some constant times T minus A. So T minus A is in fact CE to the KT, if you go back to the original equation. So yes, indeed, it's K times T minus A. So yes, it does satisfy our equation. Okay, now that we know it satisfies. Outside air temperature is 5 degrees. Heating, oh, it's pretty cold, isn't it? Heating system breaks down, oh no. So the room temperature drops from 20 to 17 in half an hour. After how many hours will it drop to 10? Okay, T will equal 5 plus CE to the KT. 5, that's going to be that outside air temperature where we've shifted that asymptote to. It's never going to drop below 5, the outside air temperature. So C will be 15 because we said C plus A or C plus N or whatever letter you're using, but those two added together will be the initial. So 5 plus 15 is 20. Now to work out the constant, we know after half an hour, temperature has dropped to 17. So subbing that in and playing around with it, getting K the subject, there's our constant, 2 log 12 on 15. Well, actually, I suppose we could simplify the 12 on 15, couldn't we? But anyway. So now, when T equals 10, so you can see it still, yet again, is more just substitution. Playing around with it, again, we get 1 on K, log of a third. K is the one we just worked out. It works out to be around 2.46167. So 2.5 hours, I said on that one. It's interesting because it did say after how many hours. So like, do you write after 3 hours?
Yeah.
I mean, 2.46 was so close to 2.5. I thought
What is it?
it seemed a more.
Because it is after 2 hours.
Yeah, it has to be after 2 because we said it's happening at 2.46. So at 2 hours, it hasn't happened yet.
But can you write like between 2 and 3 hours?
Yeah, I guess. Look, I think as long as you got that t equals 2.46167, because then they know you have calculated it correctly.
It's not after 3 hours. It's before 3 hours.
Well, that's why I said 2.5. But even then, 2.5,
It's before 2.
exactly. That gives a logical explanation of your answer. It's going to be okay. They're more interested in the 2.46167 that we got to that, is what they say. All right.